So here's the object on an incline, some angle theta, which they have prescribed as 30 degrees. They give us a coefficient of friction, kinetic coefficient of 0.25, and I'll talk about that in a moment. And then we have a pulley system with a cable fixed up here, and then coming off that cable is some force P, which happens to be at another angle 30 degrees. And the object happens to have a weight of 100 pounds. Okay. Is this a free body diagram? No. No, it's not a free body diagram. So what we want to do is free the body from everything that's attached to, and then place the forces on there. So what we have is cable tension. Now, if the pulley, let me draw on a large picture of the pulley for a second. If the pulley has some tension coming off of it, force P, and it comes in here tangent to the curve. There's a point of tangency there. Let's actually draw that better. And then coming out here is a force. Now imagine that for a second that we sum the moments about the center of this pulley. Sum the moments about the center of this pulley. So we know the force P on its lever arm R, and those are perpendicular. If there's no friction in this pulley, then doesn't the force over here have to match that force? Otherwise the pulley would be unbalanced in its tangent forces and the pulley would spin, right? So if you sum moments about the center of a frictionless pulley, then that means that the tension on both sides have to be equal. Otherwise it would accelerate in rotation. And that's not the case here in this problem. Okay, so we have force P given here. That means that the tension here has to be force P. And then we come back over here now and take a look at this. And oftentimes what I'll do, I mean, that's pretty obvious. So you aren't going to be writing drawings like this all the time. What you're going to do is just do this. Well, the pulley's accelerating, but it's not in rotation. Well, it is. I'm sorry. Thank you. It is. But we're assuming the mass and the rotational moment of inertia of the pulley is 0. Okay. So we're assuming this is a massless pulley. So you guys are getting picky. You've taken too much physics, I think, or something. Okay. I'm training you to be engineers. Get a little looser about it. Okay. So we're assuming a massless pulley, and this is reasonable for many engineering calculations. So we come in here, and how much force is now pointing up the ramp? That's the reason I asked.
Parallel to the ramp?
Parallel to the ramp.
P plus cosine 30 degrees.
P plus the adjacent edge of this piece of force. So there is P plus P cosine 30 degrees up the ramp. Just a second, Daniel. And then there's another piece of that force that, keep in mind, imagine this isn't even, imagine this is, this, how are we treating this whole thing here as a particle? We're treating this whole mess here as a particle. Okay, so keep that in mind. Everything's centered at one spot. So there's another piece of the force that points perpendicular here, and that's P tangent, or excuse me, P sine of 30 degrees. Now, what does that component tend to do to the object that rests here on this ramp? It reduces the contact force, the part of the body weight that is pushing against the ramp. Okay? Saw a hand up.
Yes. I'm not sold that we don't want the pulley to spin. Because if we pull...
No, we do. I misspoke.
Okay.
Okay.
So how can our assumption hold there?
We want it to spin without
Pulley
accelerating.
spins, it's massless, it's got zero moment of inertia, and it's essentially a point. Okay?
Okay.
So imagine it's not even a pulley. Imagine it's just a little wrap. The cable just goes around a little micro wrap with no friction in it or anything. Then all you've got is effectively these forces acting on your particle. Keep in mind, we're talking about this whole mechanism as a particle. Okay? We're just drawing it big so that we can sort of have something to grab a hold of.
We balance the torques on the pulley because we don't want to think about it accelerating.
Actually, the pulley does accelerate. I should have just, if this is court, I'd just say strike that from the record or something like that, okay? Right, back up the DVD if I could and remove those remarks, okay? So it's just, we're treating this whole thing, whole mechanism here as if it's a point, and we're dealing with the unbalanced forces that are acting on it and trying to see what happens to it, given the description, what they want us to do to with the problem. Does that make sense? Okay, good. So you guys got to keep me on my toes, and I'm glad you catch me on those things. Okay. So now, I'm not done with the free body. We now have the weight here. And keep in mind that this embodies, when I say 100 pounds in our American units of measure, that includes the mass times the acceleration due to gravity. I will never do problems where I give you a mass in slugs. That's the most archaic unit of measure. I don't mind saying it on camera either, okay? And we should get rid of that whole system of measure, but our government has just been hanging on to it. We're the only country in the world, I think, that still uses it. And so you as professional engineers are going to have to be dealing with a metric system for sure, and you've been getting a lot of exposure to it in many of your courses anyhow. So anyway, enough said there. Am I done with the free body? Not yet. We have a component of force exerted by the ramp against the object, and we typically call that the normal force. Am I done yet?
Friction.
No. Friction. Friction always is in what direction?
Opposite the direction of your...
Opposite the tendency for motion. Opposing the tendency for motion. So I think they told us in this problem they want this thing heading up the ramp. Yes. So we're going to place a friction force down the ramp. I'll just call it F. Feel good? Okay. So we now have a nice drawing here. Is that a complete free body diagram? Oh, I guess I need a little geometry. I need some...
Yeah, it's complete in the sense you have all
Yeah.
the forces, they're just not...
Yeah. So we have this angle right in here, which happens to be 30 degrees.
Right.
Because it's nice to make your free body diagram so you don't have to look hardly anywhere else to start writing your equations. And I'm being real careful on this one with you, just to impress you with that importance of it. Now, in the dynamics problem they have given us, you are going to assign what to F, the friction force, based on your background? Mu times the normal. In other words, the coefficient of friction times the normal force. Let's just do that at this point. How many of you are pretty shaky on that? Anybody? Okay. I'm going to explain on another problem in more detail why, where that comes from, just to make sure that it's really in your brain there, okay? And it didn't slip by you in some previous course, okay? Maybe I should do that right now. Probably so, because there's lots of problems involving friction. Okay, let's pause. Let's say, I'm going to go over to this other board. Let's say we have an object and we apply some force P to that object and it's on a resisting surface. So there's going to be an opposing friction force. I'll call it F. Now, there is a weight of this object on this surface. So we'll call that mg. And what we want to do is track as we let P grow. Actually I'm going to go the other way with it. I'm going to let my friction force be plotted as a function related to P, the applied force P. If P was 1 Newton, 1 Newton of force, which is about 1/4 of a pound, a Newton of force, then what would be the friction force?
Depending on its static kinetic.
Okay, let's say it's on a pretty sticky surface. You apply a Newton, and then this force would be probably a Newton, right?
Okay.
1 Newton, 1 Newton of force, 1 Newton of friction force. 2 Newtons, 2 Newtons of friction force, equal and opposing. Is that thing going anywhere? Not as long as these forces match each other. Not as long as these forces match each other. It'd be going right up at a 45-degree angle if the scaling on both these axes is equal. Right? 45 degrees. Eventually, that bond right here is going to pop loose. Will pop loose. And that's some critical friction force. Okay, so there's a critical force there at which this thing pops loose. Now think about what that would look like if I look at the combination of these two vectors right here. If I draw those, I have a downward, actually what I'm going to do is I know that what's acting upward here? The normal force. So if this object is resting on a horizontal surface, then that normal force is going to match the weight. Okay. What I want to plot is I want to plot that normal force, which I'm going to hold as a constant, and I'm going to let this friction force build up. Little bit starting, more, until it reaches this critical value. That value means that there is a resulting force on this object that is in this direction, the combination of the normal and the friction force. It is up and tilted back a little bit away from the tendency for motion. The tendency for motion created by force P is to the right. This force will gradually grow until this thing reaches a break loose point. Now, in the theory of Coulomb dry friction, your contact surface, and the book may talk about this, you could think of it as having irregularities. The object up above, if you look at the surface in a microscopic level, has irregularities. So the theory, and again it's theory, it hasn't been totally proven, is that when these things are kind of locked in there like little teeth, even possibly at the molecular level, or a rougher surface physically where you could actually see it pretty easily. And so, or there might even be a molecular bonding kind of going on between them. So what happens when you start pulling on this object, you're going to cause this to pop loose, and then the theory says that these things are then going to pop loose, and then it's going to take a little less, this has been shown experimentally, then to keep it moving, the force actually drops off a little bit, the required friction force. And so what happens then, it holds at a lower level. It holds at a lower level. So what's this coefficient of friction we call mu? It is related to this breakaway angle right here. The tangent of this angle, which is this critical force divided by that normal force, is what we call mu. That's what we call mu. So this critical friction force then is going to be equal to mu times the normal in value. That's where it comes from. So think of this tangent of the friction angle as being this Greek letter called mu. If that force is dropped off a little bit, then you're going to get a lesser coefficient of friction, a slightly lesser coefficient of friction. And that's why we use different subscripts, mu static and mu kinetic. This is what's needed to cause it to break loose, and the kinetic is after it's in motion. So it's probably appropriate to go ahead and go through this discussion with you a little bit. I've got another thing I'll say about this, but I think I'll wait till later.
Is there any particular reason to use the normal with NG?
Yeah, because sometimes it's not mg. Yeah, John's question was, is there a particular reason why we don't use mg right here for the normal? Example, look at this problem right here. This normal force, when we sum our forces in this direction, that normal force is not going to be equal to mg. For two reasons. One is we're on an incline, which is going to reduce the amount of the weight that is pointing that way. Does that make sense? And also, we have a piece of this tension that is wanting to lift this particle, I keep saying, up off the ramp, which would tend to reduce the contact force as well. Okay? So here we have a pretty picture now, and we then make this substitution that the friction force is equal to the mu kinetic times the normal. Feel good? Is that a complete free body?
Yes.
It's very, very close to being complete. What I would like you to always include is a coordinate system on which you then write your equation, based upon which you then write your equations. Very, very important. Now, since the motion is up the ramp given to us in this problem, I think I'll just pick that as x, and in the traditional fashion, coming off away from the ramp, up above the ramp, call that y. Yeah?
So do you want the free body diagram drawn of the object in the original position, or can you just draw the free body diagram in the coordinate system that you choose?
Well, what do you mean by distinct?
Well, I mean, did you have to draw the free body diagram that way? I mean, you could have drawn it level in the coordinate system that I chose.
I think it's going to be useful to you to draw it like I've shown it. The reason is you're going to see frequently that I may want you to allow for this angle to be variable and come up with a generalized design formula that would work for any ramp angle theta. That makes sense? Because that's what you folks as engineers are learning, is how to formulate, either for design purposes or for different types of applications, where you might hand some equations to somebody and tell them use these equations or these formulas, and then go out there and do some analysis and then see if the results of these formulas match up with some experimentally derived data. So we will frequently generalize this kind of thing. Okay.
Draw it in its original position, shape, or orientation, I should say.
I would highly recommend that. Okay, so you've all done problems like this in physics, but it never hurts to go ahead and crank out a few of these, and I think I've assigned some similar to this. So if we would, what direction might be the best to write our equations first? Normal, in the y direction, or in the x direction? Yeah, because the y direction, it's constrained motion, isn't it? It can't move in the y direction. So writing that is going to give us a value probably for this normal in terms of maybe related to p. So then we'll always write your governing equation so you are explaining to someone what you're doing. So writing sum of forces in the y direction equals mass times y acceleration. And so then we look at this, and I see a positive p sine theta, or sine 30 degrees. I have a positive n. And then in the negative direction, I have a minus 100 cosine 30. I believe that's the sum. That sum is equal to the mass times the acceleration in the y direction. Acceleration in the y direction is 0. So please, I would really encourage you to write this down and then put a line through that and call it 0. And you could even write an English comment in here, since ay equals 0, since no motion perpendicular to the ramp.
Wouldn't there be if you pulled hard enough on the cable?
But for the sake of the problem.
Yeah, for the sake of the problem.
Yeah.
Okay. Yes.
Didn't we agree that the magnitude of that first point to the right was just equal to p plus p cosine 30? That p sine 30 is tripping me up. I don't like p.
I'm writing equations in this direction.
I know, but we found the magnitude in the x direction on the pulley.
Yes.
So why is there a component of the y? Yeah, but that's not acting on the
Doesn't this p break up into two pieces?
well, yeah, but that's acting on the pulley, and all we want is the force that's acting on the. Oh, okay. You have like a rope attachment.
Yeah, so rope attachment there. And keep in mind, once again, you had to do this in strength of materials, those who took that course. You were looking at stress and strain at a point in a material. At a point in a material, and you would frequently draw boxes and triangles and things like that to see what the stress and the strain were in different directions. You're really talking about there a point, a microscopic point location inside a material. We're doing the same thing here. We've got P, and we have P cosine theta that way, and then we have a P sine theta there, and we have a 100 pounds here, and we have a normal force there, and we have a friction force there. But we usually are going to draw some kind of a little box just to give us a little more sense of what we have. Could be an automobile, could be an airplane. Okay. So this is really what's going on right here. Okay. Then, so this equation now simplifies, and so we have P over 2, because the sine of 30 degrees is a half, plus the normal force, minus, this is square root of 3 over 2, so minus 50 square root of 3 equals 0. So our normal force is equal to 50 square root of 3 minus P over 2. An intermediate result that we're going to need. Writing now the sum of forces up the ramp, mass times acceleration up the ramp, the sum of forces in the x direction is P plus P cosine 30 degrees, right, so far, minus mu k times the normal, that's our opposing friction force, minus 100 sine of 30 degrees is the component of the weight that is down the ramp. Is everything here on the left side? Does that cover it? If you look at the free body over there? Okay. And that's equal to the mass of the object times the prescribed acceleration, which I believe they gave us. 5 feet per second squared, so that's going to go in right here. We also can substitute in our expression for n. All right? So here we go. We have P factored out right here with a factor of 1 plus square root of 3 over 2 for the cosine of 30 degrees. And in here, we're going to input our expression for that normal, which was 50 square root of 3 minus P over 2, all times your coefficient of friction. So if I'm careful, I usually write every detail out just so I don't mess it up, but notice that this negative on this term and that negative on P turns positive. And then if I have the P factored out in one step, I'm then going to have a positive mu k over 2, I believe. Is that correct? Okay. These other terms are constants, including the 50 radical 3 times the mu. So we're going to kick those terms over to the other side, and so we're going to have 100 sine of 30 positive plus 5 times the mass, and the mass was 100 pounds divided by 32.2. And then we also have to bring over this negative term here, mu k times the 50 radical 3 becomes positive to the other side. Positive mu k times 50 radical 3. So I believe they were asking what's the prescribed force in this problem. So the prescribed force then is going to have to be equal to the stuff on the right divided by this factor we have right here. So we're going to have 50 for the sine of 30 times the 100 plus our 500 over radical 3. I'm sorry, 500 over 32.2. Plus our coefficient of friction, which they told us was 0.25, times 50 radical 3, and that divided by 1 plus radical 3 over 2 plus 1/4 times a half is 1/8. And if we punch that on the calculator, we should get so many pounds of force.
43.8.
43 point what?
8.
43.8 pounds of force. Now, what we could do, if you write every step out, and I've mentioned this before, if we write every step out, we could and we left the 30 degrees in throughout our work, we could come in there and then generalize that by calling this theta, and carry that right all the way through to our final formula, and then we would have a generalization for P as a function of ramp angle theta given the acceleration equal to 5 feet per second squared, if that's what we wanted, and a mu factor.
So not all your
And-
thetas are going to be your ramp angle, because unless you know for a fact that your P is going to be 30 degrees to the ramp.
Yeah, and we could even generalize that. We could have called the ramp angle, or not the ramp angle, but the angle that P was at, not 30 degrees that happened to match the ramp, but we could have put in at some other angle called beta maybe, and come up with a generalized formula for this type of mechanism. Okay? I think we're just about out of time for today. So what we'll do, this is the way to do it, is you draw a free body diagram very carefully, double check to make sure you got it right, put the given information down there with your work, and then start writing your governing equation and then carry on through from there. Okay. Quiz, I'm going to have a quiz for you folks that you'll be able to take anytime after class tomorrow and before class Thursday, by class time Thursday. And you can come to the Math Resource Center anytime. They're open tomorrow night, they're open Wednesday night in the Resource Center, they're open all day Wednesday as well, and they're open all day Thursday before class.
Anytime between.
Yeah, I'd say allow yourself an hour. It's just a short quiz, 20-point quiz is all, so it's not real serious points-wise, but I want to check and see if you've got your kinematic skills down. Could be anything, fair game.
What's the quiz up through the end of chapter 2?
Not constrained motion. It's on kinematics of particles, and it'll be two-dimensional. Okay,
No
All right.
notes.
Thank you for the warning on that.
yeah.
No notes on there.
It's
I don't know what.
No notes.
No notes. I'll give you some.